Welcome to class 3 on solid state devices. In this class, we'll learn about effective mass, energy band diagram, then direct, indirect band gap semiconductor. Uh, we'll discuss about effective mass. Any atoms inside a semiconductor or inside a material having some binding energy, and this binding energy depends on different characteristics of material. Then depending on this binding energy, mass of electron can change uh, for different situation. Mass of electron can appear different. It is relative. Actually, electron mass is going to be fixed, but thing is for different situation, relative effective mass, relative mass of electron can vary. Then we will discuss about wave number, about spatial wave. Then momentum of electron, will calculate that. Then velocity of electron, uh, effective mass calculation, then particle in conduction band, particle in valence band, and particle in transition. Actually, when on particle, maybe electron lies inside valence band or conduction band, its relative mass get varied because of that binding energy. And when an electron is traveling from valence band to conduction band or vice versa, then also its effective mass get changed relatively. We'll discuss that thing here. Then structure of energy band. Uh, I said energy transition of electron from direct and indirect band gap semiconductor. Then we'll go for some kind of illustrative example here. That's what we'll discuss today. So let's consider one electron inside a material having some net force on that is F net is equal to F internal plus F external. Means internal force due to this binding energy and external force applied externally in form of maybe some potential applied externally, or maybe heat or some another kind of sources. So total force acting, let's consider you have a semiconductor material, you are applying some potential, external potential on it. So what will happen? Electron due to this external potential will get some energy, but the energy whichever you have applied externally, the entirely will not acted on the electron to accelerate it, unless some energy will get wasted due to removal of electron from its binding forces. So let's consider you have applied some external voltages to some material, maybe metal or semiconductor, whatever it is. Due to that, this electron having mass m is getting accelerated with the acceleration of a. Fine. So m into a is your total force applied is F internal plus F external. Now considering internal force as 0, now what will happen whenever we will calculate the forces on electron? We can measure the acceleration, but we can't measure in the binding energy practically. So thing is, we have to adjust that binding energy somehow. So that is being adjusted, because whenever you are applying some force, electron is getting accelerated, and that velocity is comparable to light velocity. So your effective mass of electron is never going to be fixed. So that internal force whichever get wasted due to um, uh, overcoming the internal binding energy of that electron is being adjusted inside the change of mass. So now m star of A is equal to F external plus 0, we have considered internal force which get wasted due to uh, overcoming this internal binding energy. We are considering this zero, and we parallelly we considered that amount of force is converted into mass as the particle is moving some velocity which is comparable to light velocity, and that masses get adjusted inside the change, that forces get adjusted inside the change of mass. So that mass is called effective mass, m star. So m star is called effective mass of electron. Let's consider me star is the effective mass for electron and mh star is the effective mass for holes. Okay. Now what about wave number? Wave number, you consider a spatial wave. You can consider a wave in some coordinate amplitude versus time, but this wave is not in that form. It is amplitude versus distance form, called a spatial wave, and as many number of complete revolution you are having within some particular length, say 1 meter or 1 centimeter, that number is called wave number. So wave number is the number of complete cycle a spatial wave travel per unit length is called wave number. So wave number k is defined by 2 pi upon lambda. Wave number is k and lambda is the wavelength of that wave. This is also called a wave vector, and wave vector having equal dimension and very analogous to electron momentum. So somehow we'll use electron momentum and wave number for similar meaning. We'll show in some time later that this wave number and electron momentum having equal dimension. Okay. Now let's discuss about electron momentum. So according to Einstein's equation, E is equal to mc square. If we apply this equation to electron velocity, because as I said, electron is moving at some velocity which is very comparable to the velocity of light. So I can write for electron movement, for electron velocity, I can write E is equal to mv square, where v is the velocity of electron. From Einstein's equation, E is equal to mc square. Again, E is equal to h nu. H is the Planck's constant and nu is the frequency of radiation. So this is this two equation is equation of energy. So we can equate this thing, h nu is equal to mv square. I can rewrite this mv square by mv multiplied by v, and you know mv, m is the electron mass and v is the velocity of electron. So mv is equal to momentum p, equation number 1. Now v is equal to nu lambda. Nu is the frequency, lambda is the wavelength. So velocity is given by nu times of lambda. Now h nu is equal to p, and in place of v I am putting nu into lambda, or h is equal to p times of lambda. If you cancel this nu out from both sides, so h is equal to p times of lambda. So p is equal to h upon lambda, means momentum is equal to Planck's constant upon wavelength. Equation number 2, very important. Now we know that wave number k is given by 2 pi upon lambda. So lambda is equal to 2 pi upon k. If you put the value of lambda in equation number 2, you will have hk upon 2 pi, p is equal to hk upon 2 pi. Now is equal to, that is equal to h cross k, where h cross is equal to h upon 2 pi, called normalized Planck's constant, h cross. So this is equation number 3, p is equal to h cross k. Now, as I said, H is constant called Planck's constant. So H cross means H upon 2 pi is also a constant. So P momentum proportional to K. That's what I said earlier. Electron momentum means P, and wave number k or wave vector k having equal dimensions. So somewhat we different times we will use wave number or wave vector and electron momentum for similar dimension and similar meaning sometimes. Now electron velocity is equal to half mv square. So mv square. So I can rewrite this equation by I'm multiplying by numerator and denominator by m. So it is mv square. M square v square means mv square of that upon 2m. That means mv means p momentum. So p square upon 2m. And as I said, we have derived in equation number 3, P is equal to H cross K. So I'm putting the value of P here. So H cross K square of that upon 2M means H cross square K square upon 2M. So E, energy having the dimension of H cross square K square upon 2M, equation number 4. If we differentiate this equation with respect to wave vector, dk is given by h cross square upon 2m into 2k is equal to h cross square k upon m. So h cross k into h cross upon m, and you know h cross k is equal to p. So h cross into p up divided by m. So dk is equal to h cross p upon m. So dk is given by, if we put the value of p is equal to mv, then you will have will get cancelled out. So you will have h cross times of v. So v is given by 1 upon h cross into dk. Electron equation of electron velocity in differential form, 1 upon h cross into dk, equation number 5. Now, how electron mass can be given in the similar form? So we have something dk is equal to h cross v. We are starting from here. dk is equal to h cross v. Now h cross v means h cross square upon m into k. Look here. This is h. Okay, h cross square k upon m. Start from here. dk is equal to h cross square k upon m. H cross square k upon m. Now, if we further differentiate that, d2e dk square is equal to h cross square upon m. So m is given by 1 upon h cross square d2e dk square, and any effective mass from 1 upon m star. If you consider the effective mass, so it is given by, effective mass is given by 1 upon m star is equal to 1 upon h cross square d2e dk square, equation number 6. This is a differential form to calculate effective mass of an electron. Now, as I said, an electron is traveling at a velocity which is very comparable to light velocity. So its effective mass, its mass get changed. So relative mass get changed because it depends on energy. Because energy and mass at that velocity is analogous thing according to Einstein's theory of relativity. So particle in conduction band, if any particle lies inside conduction band, what will happen? As we know, conduction band having some extra energy. That means any electron which is inside conduction band having higher energy than some electron lies inside valence band. Now, if you can recall equation number 4, energy is a function of k square. You know, h cross is a constant, normalized Planck's constant. M is also a constant. So energy is only a function of k square. So any electron, it may lies inside a conduction band or inside valence band. Wherever it lies, it's supposed to be the function of k square only. So let's consider some electron lies inside conduction band at this position, say C, at some positions. So C at some point C is supposed to be a function of k square. So some energy, so if any electron lies inside in the conduction band and some point C, so we can write E minus EC. E means some energy inside conduction band, E inside conduction band. So we can write E minus EC is equal to C of k square. So E is also a function of k square, and C is also a function of k square. C is some constant energy point inside conduction band. So if we differentiate this equation, d dk is equal to d dk minus 0. You know, EC is a fixed level of energy, so differentiation of that is 0, which is the conduction band minima. So C is equal to C on of 2k. As C is a function of k square, C on is the first order derivative of C, is also a function of k square, is a function of k only. And if we further differentiate this, d2e dk square is equal to 2c2. C2 is the first order derivative of C on, or second order derivative of C, which is a absolutely constant, not function of k. Now from equation number 6, if you consider this equation number 6 and put the value of this second order derivative here, 1 upon h cross square is equal to d2e upon dk square is equal to 1 upon m star. Then 1 upon h cross square into 2c2 is the value of d2e dk square is equal to 1 upon m star, or 1 upon m star is greater than 0, and m star is also greater than 0. So this mass relatively appears, m star means relative mass greater than 0 means any electron inside conduction band appears as heavier. It's called heavy particle. So any electron inside conduction band called heavy particle and having some tendency to go downward, means any electron inside conduction band having usual tendency to lose its energy somewhere, and tendency to go to valence band. If particle lies inside valence band, what happens? As I said earlier, any energy is a function of k square. So any particle lies inside some other point C here is also a function of k square. So we can write that the similar equation, EV minus E is the energy of EV minus E is the energy, some haphazard energy of the electron lies inside valence band. So EV minus E is equal to C of k square. So some point C, so energy minus energy is also energy, and this is also function of k square. And if you take first order differentiation of that, then 0, if is a fixed level, that is a valence band maxima. So 0 minus d dk is equal to C on of 2k. C on is the first order derivative of C. is a function of k only. So minus d dk is equal to c on 2k, or even simply c on of k means function of k only, and d2e dk square is equal to minus 2c2. C2 is a second order derivative of c, which is constant, not a function of k. So d2e dk square, if you put the value, same value from in equation number 6 again, you will have m star less than 0 means any particle inside a valence band appears as a light particle. This is called light particle, and having some tendency to achieve some energy from somewhere and go to conduct and jump to conduction band. Then if we consider energy band diagram, which we have drawn earlier in this type of figure, conduction band is flat one, or valence band is flat one. This thing practically never going to be like that. Conduction band in this type of parabolic shape. Valence band is also some parabolic shape again, and difference between this valence band maxima to conduction band minima is going to be Eg, but this thing actual shape should be in parabolic form, and electron momentum or wave vector along this x-axis, and energy along this y-axis. This is the actual structure of energy band diagram, or more precisely EK diagram, as this is energy E versus wave vector or wave number K, or even electron momentum. As I said, electron momentum and wave number having similar dimension. Okay. Now, if we consider transition of electron from valence band to conduction band or vice versa, and if we apply energy conservation here, EI is the energy, some electron, let's consider some electron inside this valence band having some energy state EI. Now, it have to go to some energy level EV, then and only then it can jump to conduction band. It is having some energy from photon. Initially, it was in EI energy state. Then from EI it will go to EV. Then from EV, if that photon energy is sufficient enough, then it will overcome the energy gap of EG, and then it will go somewhere, some final destination of EF, some higher energy level than conduction band minima. Then within 10 to the power minus 15 to 10 to the power minus 12 seconds, that means very quickly it will lose the energy and it will come to conduction band minima. This is a different thing. We'll consider some electron in EI state. It will jump to EF state, having some energy from photon, okay, and that photon having energy of h nu. So from energy conservation, EI plus h nu is equal to EF is the final energy plus E of phonon. Means what? Whenever electron will be some higher energy state, then it will lose the energy to the phonon. Phonon means some constant and periodic jerking of atoms inside any material. Is a constant, periodic, and eternal process inside any material. So EI plus h nu is equal to EF plus h nu of phonon, means Planck's constant times of lambda. As I said, phonon is a constant jerking having some particular wavelength, as this is periodic on. So phonon is a periodic crystal vibration. Photon wavelength, lambda photon is given by 100 or sorry 1000 angstrom wavelength of photon. Photon wavelength is phonon wavelength is given by phonon wavelength is maximum it can be up to 5 angstrom. As I said, the interatomic distance in order of 5 angstrom earlier. So phonon having very less wavelength than photons. So photon energy is h cross k of photon. So h cross h upon lambda of photon is the photon energy, and phonon energy is given by h cross k photon. H cross k phonon is the phonon energy, and h upon is equal to h upon of lambda phonon. So if we compare these two, we can see phonon energy is much more greater than photon energy. So any electron which is accelerating from valence band to conduction band with some extra energy, and that energy, that extra energy is easily observable by this phonon. Now, if we consider the same situation again, some electron in EI state jumping to some position of conduction band, inside conduction band, having some energy of EF. So, for successful transition from valence band to conduction band in presence of photon, h nu, that is the photon energy, is equal to Eg. You have to overcome this Eg. But before that, you have to come from EI to EV state, because any particle to jump from valence band to conduction band, it have to jump from the valence band peak. So first of all, any electron, this electron was in EI state, EI energy state, which is lesser than EV. So first it have to come from EI to EV state, EV energy, and EI for coming from EI to EV state, you have to have some energy h cross square k square upon 2 mv star. As I said, mv is the effective mass of valence band. So that energy is h cross square k square upon 2 mv star. Then you have to overcome this Eg, plus it is not going to conduction band minima only, it is having some extra energy and going to some energy state of EF. So again another energy which is equal to h cross square k square upon 2 mc star. So if we equate that thing, h nu is equal to Eg is the energy gap value plus h cross square k square upon 2 mv star plus h cross square k square upon 2 mc star. So Eg h nu minus Eg, if I take Eg this side, h nu minus energy gap is equal to h cross square k square upon 2 mv star plus h cross square k square upon 2 mc star. So this, if I take h cross square k square upon 2 common, so it is 1 upon mv star plus 1 upon mc star. So h nu minus Eg is equal to h cross square k square upon 2 mr star, where mr is the effective mass of electron under transition from valence band to conduction band or vice versa. So 1 upon mr star is equal to 1 upon mv star plus 1 upon mc star. So this mr is the mass of transition. So if we go for some kind of summary here, when any particle lies inside conduction band, it is called heavy particle, and mass appears a bit heavier, relative mass appears a bit heavier. Thing is very clear here, because any particle lies inside conduction band, and conduction band is having very less binding energy. If you can recall, any electron, any material, any particle, any atoms having some outermost electron, that means valence electron, is the conduction band electron. Means electron having less binding energy. So as binding energy is less, if you apply some external force on that electron, it is bit easier to have acceleration from there, and your vortex of force due to overcoming this internal binding energy is less. So material appears, so particle appears a bit heavier, called heavy particle. Similarly, any material inside valence band having some higher binding energy than conduction band. So if you apply some force there, you'll get acceleration, but you have to cost more due to overcoming this binding energy. So you will have acceleration. Definitely, you will have acceleration from there, but your wastage is more. So that means particle appears a bit light particle, because that you have to combat this internal force by some wastage of mass, and mass appears a bit lighter, so called light particle. Uh, so particle inside conduction band is called heavy particle. Particle inside valence band called light particle. And under transition, so when some particle is moving from valence band to conduction band, or conduction band to valence band, that means particle under transition having some different mass called mr star, which is uh, higher than valence band mass but lesser than conduction band mass. So somewhere in between this. But ultimate thing is mass of electron is fixed, but mass under different situation relatively appears different. Now, direct and indirect band gap semiconductor, as we shown earlier, uh, that energy band diagram can be plotted. Energy versus electron momentum, or energy versus wave number. Okay. So if for any kind of semiconductor, if conduction band minima and valence band maxima appears for same value of electron momentum, then that is called direct band gap semiconductor. And if it appears for different value of electron momentum, look here, conduction band minima is appearing for some different values of k, different value of k, and valence band maxima is appearing somewhere else. That means transition from valence band to conduction band, here it is direct, but here it is not direct. Some particles say inside conduction band have to go to valence band, then what it have to do, it is in higher electron momentum, so somewhere it have to lose its momentum. So it may be in phonon jerking, it have to lose some momentum, and after losing some quasi energy state created over here, and then from there to valence band it have to go. Or reversely, if any particle wants to go to conduction band, then it have to jump from this valence band maxima to some quasi energy state here, and it have to achieve some extra momentum to go to this conduction band minima. Practical semiconductor which are available physically, silicon, germanium, etc. All semiconductor are indirect indirect band gap semiconductor. And other compound semiconductor like gallium arsenide, gallium indium phosphide, indium phosphide, all are direct band gap semiconductor uh, by nature. Now let's consider some example. Plot the energy band diagram of a semiconductor having band gap is equal to 1.6 electron volt, and energy band equation is given by E is equal to EC. This is conduction band equation. EC plus H cross square K minus 5 whole square divided by 2 MC star. This is the conduction band equation. Valence band equation is E is equal to EV plus H cross square K square upon 2 MV star for valence band. Now, if we plot this, this is not appearing. If you look that equation more carefully, it's not appearing for same value of k. That means conduction band minima and valence band maxima is not appearing for same values of k here. If you plot the energy band diagram, you will see like this. Valence band maxima is appearing for k is equal to 0, and the conduction band is band minima is appearing for k is equal to 5. So this is not appearing for same value of electron momentum. Obviously, this difference from lateral difference from conduction band minima to valence band maxima is 1.6 electron volt, but this is not appearing for same electron momentum. So it is indirect band gap semiconductor. You can comment on that. And one more thing, this valence band maxima, this um, point is having k is equal to 0 doesn't mean that wave number or wave vector is equal to 0 or electron momentum is equal to 0. This is with respect to that coordinate system. This k having some fixed some particular value, and conduction band minima is appearing 5 unit higher than that particular value. I think we should stop here today. Thank you.